For centuries, the world has constructed homes, towns, cities, and empires out of timber. Timber was readily available and easy to work with. Now our cities look like this, with huge glass skyscrapers constructed from steel and concrete. There's one huge problem with this though. Steel and concrete require the production of a lot of carbon dioxide. Not only that, but energy is becoming a scarce resource, and the world is running out of materials required to make steel and concrete. Going back to using timber could be the ideal solution to these problems. Timber can be grown so it is renewable, and as trees grow, they sequester or trap carbon, so are carbon negative. The main engineered timber product now used is called CLT. CLT is layers of planks glued together at 90 degrees to each other on every layer. This makes CLT as strong as concrete. So how do you stop the whole building from going up in flames? Well, if the building is big enough and the CLT is sized appropriately, then the CLT will catch fire, but there is enough timber to sustain the weight of the building, even as it burns. Or we can cover the CLT, or encapsulate it, in a protective layer, to make sure the CLT does not catch fire. If the CLT members are big enough, then as the CLT burns, a layer of black char forms, and this acts like the layer of protection we just saw, limiting the ability for the rest of the CLT to burn. My building needs to be big enough, because if the rooms I build my CLT from are too small, they can become feedback chambers, where the heat of one burning wall of CLT can cause another to burn more intensely, and so on and so on. This is extremely dangerous. A lot of these phenomena are poorly understood by a wide cross-section of the fire engineering community. Therefore, computer models could provide a more uniform, safe, and risk-averse solution to designing timber in buildings in the future. A possible computational solution could be using finite element methods to construct fire dynamic simulations in the same environment in combination with structural modeling. Finite element methods basically involves the definition of a large sea of tiny blocks, and each block can be modeled with the inputs and the outputs. Therefore, I can define my fire, and I can map how that fire heats up the surrounding environment, as well as heating up and affecting the structural members I have in my building. By also modeling the structural impact of that heating, my fire can be affected by the structure, as well as the structure being affected by the fire. Therefore, I can more accurately model what really goes on in my building. We would need our model to accurately predict what happens to the timber and to be valid in the way it models it. Research in this area is fast-paced, and to capture all the different nuances we'd need would be a very complex problem. To code the reality of what is going on into a computer model is the holy grail of timber design. It's a long project with many poorly understood phenomena, such as moisture, adhesive strength, and delamination. But if a model can be made which is valid, accurate, and then designers could in theory, with regulatory confidence, design buildings appropriately using CLT, reducing carbon output, softening the built environment, and providing sustainable building solutions for the world to use going forward.